Just introducing to you the idea of a distance matrix. The idea here is when you have a graph that has sort of weights given to the edges, so whether they be distances or other measurements, could be time, could be cost. But the idea is that if there's a value for an edge, then we can show that in a matrix. So unlike when we were using matrices for adjacency, where we were looking at how many connections there were between one node and another, here we're effectively accepting that when there is a connection, what is that distance? So again, very similar to beforehand, you set yourself up with rows and columns. So if you think about the fact that A, B, C, D are the four nodes, going from A to A, what is the cost of that? Well, it's 0. From A to B, it is 12. From A to C, it is 8. From A to D, it is 10. So I'm reading off the values that are available to me in, there's the 12, there's the 8, there's the 10. They're the values coming out of A to go to the other nodes. For B, does go from B to A, it's, oh, wrong pen. From B to B, it's not possible. From B to C, it is 9. And from B to D, it is not possible. From C to A, it is 8, same as the A to C. C to B is 9, the same as B to C. C to itself is 0, and C to D is, now there's a direction here, so the direction that allows me to go from C to D is 7. D to A is 10. D to B, it's not possible. D to C, well, that's in the other direction. I've got the direction for 6, and D to D, there's no loops there, so that's 0. So that's my directed matrix, so my distance matrix for a graph that is, well, it has some directions in it and some not, so there's not a complete symmetry. You can see that the 6 and the 7 are not the same. Everything else is symmetrical, but the 6 and 7 are not, because depending on whether you're going D to C or C to D, there's a difference in the distances. Now, as I said to you, it may not be distance, it may be another cost or value, but that's what we call it. We just call it a distance matrix. Going on to the next one here, just for the sake of completeness, if I go through this, I've got E, F, G, H, and I. E, F, G, H, and I. E to E is 0. E to F is 5. E to G, not possible. Now, by the way, it is possible. I go to E to F and then I go from F to G, okay? But not directly from E to G. So E to H, not possible. E to I, it is 7. And if I carry on going through that as a process, then we have H to E is not possible. H to F is 6. H to G is 8. H to H, well, in this instance, it is possible. There's a loop here, so there's a 3. If you notice E to E, F to F, G to G were not possible, but H to H is possible. There's a cost of 3. H to I is not possible. I to E is 7. I to F is 9. And then I to G and H and I are not possible. So there is my matrix for that graph. So you get the idea, okay? I'm not even going to bother going through this last one, but I will just put up the solution for your benefit when I upload the PDF.